Recording.
Hello everyone, I am Dev Kiran Kumar and my ID number is 2000030. Today we'll discuss about the topic and Adam optimization, which is the best optimization technique in deep learning. So let us start without wasting our time. Revolutionizing deep learning with the Adam optimization. In this class, we'll look into theory and practice part. So these are the contents we are going to discuss today's session. So first of all, we'll discuss about the introduction to optimization in deep learning. In this chapter, we can know about how the optimization will be more efficiently in deep learning and how will be the part of how the optimization will play the part of in deep learning. So we'll go into brief overview of optimization algorithms in deep learning. Optimization is the process of finding the optimal set of the parameters for neural network that minimizes a given loss function. Um, to find the set of parameters in neural network, there are maybe so many hidden layers. So we can't find. So for to minimize the loss function, we'll use the process called optimization. And gradient descent and a stochastic gradient descent are two popular optimization algorithms used in deep learning. And not only these two algorithms, but there are the algorithms like optimization algorithms include ADAM, AdGrad, and RMSProp and SGD with momentum. The choice of the algorithm depends on factors such as the size of the data set, the complexity of the neural network, and the computational resource are available. It means uh, this type of optimization algorithm depends on the factors like what the size of the data sets and what type of the neural networks are having the complexity and the resources which are available uh, to do the this type of factors. So optimizing hyperparameters such as landing rate and batch size can also have a significant impact on modeling performance. And not only that, but also overfitting can occur when a model becomes too complex and overfits to the training data. It leads to poor generalization to a new. Therefore, the regularization techniques such as L1 and L2 regularization can be help to prevent overfitting by adding a penalty term to the loss function. Therefore, here the crucial role is played by optimization in ensuring that deep learning models are accurate with effective in the predictions. Uh, Fine-tuning the model's parameters to optimization can lead to better results. Here, we can improve the overall performance of the system. As a deep learning continues, the advanced further research into the optimization algorithms uh, will have the drive even greater improvements in the model performance. It continues to advance and the further research also. Now, let us discuss what is the motivation for using Adam optimization. In deep learning, for using Adam optimization, we mainly see that the efficiently handles large-scale neural networks with many parameters, where it combines benefits of EdGrad and RMSProp algorithms by adapting landing rate based on the first and second moments of the gradients. Not only that, but also it converges quickly, effectively to a minimum of loss functions. Even in the presence of noisy and sparse gradients, it converges and very quickly to minimize the loss function. And it robust to hyperparameter choices and requires less tuning compared to other optimization methods. Now let us look into overview of the optimization, Adam optimization. What will be the overview of the Adam optimization? And Adam optimization is an extension to stochastic gradient descent, which can be used in place of classical stochastic gradient descent to update the network weights more efficiently. We can update the network weights more efficiently by using Adam optimization in the place of classical stochastic gradient descent because it may be minimize the loss function. The name Adam derives from the phrase adaptive moment estimation, which refers to the way that algorithm calculates the adaptive learning rate for each parameter. Essentially, Adam combines the advantages of two other stochastic gradient descent algorithms, EdGrad and RMS, which can be known as the Adam is a combination of EdGrad algorithm, optimization algorithm, and RMSProp algorithm. Like AdGrad and like AdGrad optimization algorithm, here the Adams maintains per parameter learning rate that adaptive over time based on the historical gradients for that parameter. However, unlike the AdGrad optimization algorithms, but Adam also keeps an exponentially decaying average of past gradients similar to the RMS problem, which means that the algorithm can handle sparse gradients or noisy problems. Uh, Adam on optimization algorithm is known for its fast convergence rate ability to handle non-stationary objectives, which cannot be done by at-grade optimization algorithm, but also it making it widely used in deep learning applications. Now we'll discuss about how Adam optimization works. In this picture, you can see that how the optimization algorithms will be worked. Here we can it minimizes the loss function. Optimization algorithm stands for adaptive moment estimation is another method that computes adaptive learning rates for each parameter. In addition, In addition to store and exponential decaying, average past of the squared gradients like Ada delta and RMSprop. Here, the Adam optimization algorithms also keeps an exponentially decaying average of past gradients like similar to the momentum. Uh, this Adam optimization algorithm can be viewed as combination of Edgrad and RMSprop algorithm, which works on sparse gradients and which works well in online and non-stationary settings and respectively. Adam implements the exponential moving average of the gradients to scale the learning rate instead of simple average as an ARGAT algorithm. Uh, Adam optimization algorithm keeps an exponential decaying average of past gradients. Here is the step-by-step working progress of the Adam optimization algorithms. Here, the first A picture can be described carry over momentum and sum of the gradient to the square from previous iterations. And then it moment and square the decay and take the gradient at the position of the ball. And we can see the explanation steps what are involved in the next slide. The given image in the above slide describes the step-by-step working of Adam optimization. These steps are involved are carry over momentum and sum of gradient square from the previous iterations. And then it takes the momentum and square decay. Then take the gradient at the position of the ball as shown in the figure above. Next, add the gradient onto the moment and its square onto the square, which is scaled by 1 decay. Then it divides the momentum by the side of the square. Finally, take a step and a new iteration begins as shown in the previous picture. This algorithm works by computing an exponentially weighted moving average of the past gradients and their squares, which are denoted as m and v respectively. The update equation for each weight is then given by w equals to w minus alpha into m by square root of v plus epsilon, where alpha is the learning rate, epsilon is the small constant to avoid division by zero, and here W denotes that weight of being updated. This algorithm includes a bias correction step to account for the fact that the moving averages are initialized at zero. This correction ensures that the first few gradients estimates are not biased towards zero. The comparison with other optimization algorithms. While comparing with other optimization algorithms, Adam combines the benefits of two stochastic gradient descent extension and the adaptive gradient algorithm, which is known as AdGrad algorithm, which retains a learning speed parameter that improves performance on sparse gradient issues. The sparse gradient issues like example natural language issues and computer vision issues. Here, the root mean square propagation means RMS propagation are also preserved by parameters learning rates adjusted to the weight based on the average of recent magnitudes. Either it's offline or non-stationary problem, this algorithm does. Uh, Adam is different to Adam is different to classical stochastic gradient descent. In stochastic gradient descent maintains a single learning rate for all weight updates, and the learning rate does not change during the training. A learning rate maintained for each network weighted separately, adapted as learning unfolds, which computes. This method computes individually adaptive learning rates for different parameters uh, from estimates of the first and second moment of the gradients. Uh, Adam realizes that the benefits of both the grid and RMS propagation algorithms, instead of adapting the parameters of a learning based, the average first moment, as in RMSprop, Adam also make use of average of the second moment of the gradient. Significantly, these algorithms calculate an exponentially moving of the average of the gradient and then the square the gradient and the parameters beta 1 and beta 2 controlled by decay rates of the moving averages. Now we'll discuss about the hyperparameters in Adam. These are the formula These are the formula for the hyperparameters of the Adam optimization algorithms. Here m equals to beta into m t minus 1 plus 1 by beta 2 into t2. Same as well as that. Here in this picture we can clearly show that in the mathematical notation of the Adam optimization algorithms. Now let us discuss about what are the hyperparameters were used in Adam optimization algorithm. The hyperparameters like learning rate, beta 1, beta 2, and epsilon are used in this Adam optimization algorithms. Now we'll look into one by one and we'll know about each. Learning rate. Here, learning rate will be denoted as alpha, which controls the step size at the each iteration during gradient descent, a lower learning rate, which results in slower convergence but may lead to better solutions. While a higher learning rate may be result in faster convergence but may be missing optimal solutions. Beta 1. This hyperparameter controls the exponential decay rate for the first moment estimate of the gradient, which usually has a default value of zero point 0.9 as mentioned here. And beta 2. This hyperparameter controls the exponential decay rate for the second moment estimate of the gradient. It usually has a default value of 0.99 0.99 and epsilon. This is a small number added to denominator to avoid the division by 0. It usually has a default value of 10 to the power of minus 8. These hyperparameters can be tuned to optimize the performance of the model, choosing the right values for these hyperparameters, which improve the robust of the model and help it convergence faster to a good solution. Now we'll go for into the practical purpose and we'll look into the code implementation of Adam optimization. So the first step uh, in the code implementation, we need to define several variables. First order exponential beta 1 and second order exponential decay beta 2. and step size and a small value epsilon to prevent zero division. Additionally, we define m underscore WWT as the mean and uncentered variance from the previous step of the gradients of the weights and biases DW and DD. To test, so um, we in this code we have defined Atom optimization, which we are in this function we have defined several variables like a first order exponential decay, beta 1, second order exponential decay, beta 2, and step size n. And therefore it last and therefore here we have done a bias correction and we have updated the weights and biases value where it returns the weights and the biases value. And here the second step. To test our implementation, we'll first need to define a loss function and its respective gradient function, gradient function. Here a gradient function can be obtained by simply taking the derivative of the loss function. For example, we look into the below given code. Here, if we look into the code, the gradient function has been obtained by simply taking the derivative of a loss function. So here we have to note that important point that we also define an additional function to check the convergence based on the fact that weights will not change when convergence is reached. So whenever the convergence is reached, the weights will be not changed until the convergence is not reached. The weights can be changed until the convergence is reached. So finally, we can iteratively update the weights biases using our constructor Adam optimization and seeing if they converges. Let us look into the what the output we got. So if we look into the output we got, after so many iterations, the result, the convergence has reached under 750 iterations, where the convergence is reached and the weights will not change at the iteration 746. So we'll discuss about the advantages and limitations of Adam optimization. There are advantages of Adam optimization like this algorithm is fast convergence, which means it uses adaptive learning rate, which means it can convergence quickly to optimum. The Adam optimization tends to generalize well, meaning it can handle unseen data well. It works on like a large data sets and compute gradients using a small batch of examples at a time. The limitations of Adam optimization, it requires tuning. Atom optimization has several hyperparameters that needed to be tuned, such as the learning rate and beta parameters. And Adam optimization is sensitive to noise gradients. If the gradients are very noisy, Adam optimization may not perform well. Can get stuck in local minima. Like all the optimization algorithms, Adam optimization can get stuck in the local minima, which may prevent it from finding the global optimum. So we came to the end of this session. In conclusion, the key points about Adam optimization algorithms we have discussed. Adam combines the advantages of two other popular optimization algorithms, AdaGrade and RMSProp. Adam also adapts the learning rate for rate of each parameters during training based on the first and second moments of the gradients. Adam uses biased correction to reduce the impact of the initial estimates of these moments. And it is well suited to large datasets and high dimensional parameter spaces. Adam has become one of the most commonly used optimization algorithms for deep learning due to its fast convergence and good performance on wide range of the task. And this is the about the Adam optimization. After reading After this session, we'll able to know what the Adam algorithms is and what are the benefits of using the methods to optimization our models, and how the Adam algorithm works and how it is different from the related methods AdaGrade and RMSProp. And another question like how the Adam algorithm can be configured and commonly used configuration parameters. So for these three questions, we uh, we understood from this session. So thank you.